Welcome back to our YouTube channel, Becoming a ROS Developer. I'm Desire, and today we've got Mario, who has completed the course ROS2 Basics using Python, and he'll be giving us a presentation on that. So, without further ado, let me hand over the platform to him so he can begin his presentation. All right.
Okay, perfect. Well, everyone, nice to meet you. What I'm gonna do the following, I'm gonna show you kind of the project, how I tackled it, and sort of the challenges that I found tackling the project and how I've solved them.
Mm-hmm.
However, I think what's best is where we start with showing kind of how the robot works in real life, just to ensure that everything works appropriately.
Mm-hmm.
Um, so for that, let me download, build the relevant packages while we wait for the for us to connect to the Barcelona lab. Um,
Yeah, it
okay,
might take a bit
it's
longer
taking
than
longer than usual.
yeah.
Yeah. Okay, perfect. What we'll do to make this interesting, the idea of the of this challenge is for a robot to complete a full course of this circuit. What I'll do to make this a bit more interesting is I'll put the robot in a more natural position rather than here right next to the wall, just to show kind of the potential challenges that a user may have when
Mm-hmm.
trying to solve this problem.
Okay.
Uh, okay, it's taken longer. But for now, let's launch the program, and in the meantime, while we see the robot move, I'll explain kind of the code and how this whole repository works.
Mm-hmm.
Uh, so from here, we're launching it, and we'll see the robot move in a second. Okay, so this package contains three main components. It contains the autumn recorder, the wall finder, and the wall following. Each one serves a different purpose. The first one, the autumn recorder, is essentially what we're gonna use to basically measure the goal. The goal is basically to calculate the distance around the track and basically tell the robot when to stop.
Mm-hmm.
Then the second one is the wall following. The wall following essentially what's currently going on here, which is the script that we use to make sure that the robot is kind of following the outer wall and correctly navigates the circuit. And then the third one, which is the one that we start with, is the wall finder. The
Mm-hmm.
wall finder is the first package that we run that in order to make sure that we start at the correct position so the robot can end at the correct position.
Mm-hmm.
Within the wall finder, there were various challenges that arose. One is, as you can see from the circuit, there's this red wall. This posed a challenge for the robot trying to decide when the what was an outer wall and what was this red wall.
Mm-hmm. Mm-hmm.
What this allowed us to do is essentially it allowed us to so that posed a big problem. That's one of the problems that I had finding the red starting. The second challenge that I had was basically what happened if the robot started facing a corner. So if the robot starting and facing a corner, it was hard basically for the robot to basically go itself in a correct position. And then a second problem that I found a lot was basically what happens when the robot, like normally the assignment is done that the robot has to start within 5 centimeters of the starting position, and basically sometimes the robot missed that 5 centimeters. So right
Mm-hmm.
now it should take the is decreasing the distance to the start. It should reach the 0.05. No, sorry. No, it missed it. I
Yes.
think it's because it had a it had a weird start because it had to kind of block different obstacles.
Yeah, that's what I was
So
going to
let's
ask
give it
you.
an
That what was considered to be the beginning, right? So according to the way you have developed this, when does the robot start? When does it mark its initial position? After it found the wall, or
yes.
okay, All right. So,
after it's found the wall.
and how
Wait
close
a
does it have to
second.
be to
Long.
the wall for it to consider to have
It has
found
to
the
be
wall?
within 30 centimeters. Between 30 centimeters, it defines something as an outer wall, and then it has to be within 0.25 because what we allow is that how the assignment defines this is that the robot has to be within zero point 0.2 and zero point 0.3. And
Right.
what I have to make sure is that the robot is, so what I chose there is to make sure that the robot is 0.25 centimeters from the wall.
Mm-hmm. So,
Um,
so okay. You're moving it right now, but I was going to ask you, given where it is right now, would it mark the initial position? Is that point if it assumed that the red
no,
block is the
so
wall?
so so what you see right now is right now it has identified that this segment is the outer wall. So it's found it and it's rotated towards the outer wall and
Mm-hmm.
it's reached the outer wall. It reached the outer wall, now it's rotating its respective corresponding distance to make sure it's starting. And
Mm-hmm.
once it's started and it's 0.25 centimeters away from the outer wall, it starts the wall following. The wall
Mm-hmm.
finder package finishes and it starts the wall following. We'll look into the code later if you want, but I'm confident that this time it's gonna work because the starting position was more of what was expected.
Yeah, right. And
Um,
I like the way it found the wall. Right? Can you explain a bit in detail
yes,
how you differentiated between the red wall and the outer wall?
yes, okay. So how we do this is basically just by looking at the circuit itself, just to be concrete, uh, how an outer wall is essentially basically a very long segment of, it's a very long segment. There. Okay, perfect. It finished.
Okay, that's good.
It's a very long segment. So the big difference between, for example, the red wall and the outer wall, it's both in surface ways and in terms of kind of how the laser is tracking them. They're both kind of the same shape. The only difference is that the outer wall has it's bigger than the red wall. How we do this is at the beginning when the robot starts is we kind of trace all of its different obstacles around. One thing that we can how we define a wall is basically a set of kind of consecutive like laser rays, which are very similar in distance, which where the distance varies by very little.
Mm-hmm.
What we
Mm-hmm.
do then is what I do then is I combine them to something that I call segments, and I kind of what I call a segment is essentially a wall. So for example, if I see like I have 50 rays all
Mm.
within, let's say, each one within let's say 15 centimeters of each other,
Right.
then that's what I would call a segment. That's what I call a wall. The question is, okay, now I've built this walls. I do some cleaning where like I merge the segments that are close to each other. So for example, say I have a segment that's like, let's say for example, I have 360 rays, just
Mm-hmm.
to make it simpler.
Mm-hmm.
Say I've defined a segment from ray 1 to 50, and then I've defined another ray from 340 to 358.
Mm-hmm.
What's probably the case is that both two segments are part of kind of the same wall. So what I do then is if the distance away from the robot is of those two segments is the same, what I'll then do is I'll merge them.
Oh,
And then
okay. I
what
see
I
what
end
you
up
mean.
getting is in order to find if in order to find the wall, I basically end up with a series of segments. Each one is basically an outer wall, and sometimes it can be the red wall. What I then do is then go ahead and kind of go and pick the biggest segment that I find. Um, and then, okay, so now I've defined the biggest segment that I find, and now I know kind of which ray. And then I find kind of the center ray towards that segment.
Right. Okay.
Right, there's a difference. So, there's two ways to do this. Initially, what I try to do is I try to rotate, take so make sure the distance array is a minimum. The problem is the robot rotated. For example, what happened here at the beginning is sometimes the minimum distance array can be the obstacle. So that wasn't the robust approach. So what I did instead is I used kind of the autumn breeder in order to rotate, where from the once I define the outer wall, I know kind of which ray
Mm. Mm.
it's it is, and I basically calculate the yaw between the starting front in ray and kind of the wall, the outer wall ray. I calculate that yaw and I make sure that the robot turns that to that yaw. Either that can be like clockwise or
Mm.
counterclockwise. Once one has correctly turned, and it basically is, I tell the robot to move forward and to basically locate itself between 0.25 centimeters away from the wall.
Yeah, very, very nice implementation. I like the way that you looked into the robustness of it all, right? And tried to make it a lot more robust. And to be honest, it's a very, very well thought implementation. So well done on that bit. Job well done. All right,
Perfect. Thank you.
go ahead. Yeah.
No, I was gonna say another kind of few things kind of particular to a challenge and especially particular to this lab that I wanted to mention is as you can see there were like which for example these things don't appear in simulation but it's the type of things that once you test the robot in real life do appear
Right.
is as you can see from the lab the robot is held by a stick and a string just to make sure like I guess to charge it and just to make sure it correctly connects.
Yes.
The problem with this is, as you can see at the top of the robot, we have kind of the laser scanner.
Mm-hmm.
What happens here is if we're basically deciding most of our actions based on minimum distance, just to understand kind of what where the obstacle is closest,
Yes.
what can happen sometimes is that the robot picks up the this pole, this stick, as the minimum distance. So one thing that I made sure is I basically, when looking at it at the kind of a series of rays, I always exclude the 200 and 250, which is basically the rays that encompass
Okay.
that pole, in order to kind of exclude that from my calculations. Um, yeah, and normally this doesn't happen because most of my decisions are based for like between angles like on the front. So I'm either looking at the front window or the right window. So normally what happens from the back is not that important to me.
Mm-hmm. Mm-hmm.
Um,
And so,
what else?
so here's one of the questions that I wanted to ask you towards the beginning. So, when you started earlier, right, you're trying to show that what happens when you have your robot in a position that is, I'm going to put not normal in quotes here because let's say it's
Mm-hmm.
facing the obstacles that are movable, right, in the center there, right, and I could see that it was doing some form of sorting, right. However, there was almost very little attention that was given to trying to avoid them, or maybe it was. But can you tell me what you think your implementation might be failing there, or what is the stance of the obstacles that makes them maybe slightly difficult to detect for the robot?
I think the biggest problem with that case is, for example, if the robot were to start here, is the case. I mean, here it would kind of find a gap. Let's try. Here would kind of find a gap
Mm-hmm.
where, in order to move. The problem is, for example, what happened at the beginning, where like all the obstacles were together. What it would have a hard thing around is when, but basically, once it's found the outer wall, trying then to create a path, a navigation path,
Yeah.
basically to um, kind of contour those obstacles and then to arrive to its initial position. So that's kind of where it would fail. Like what's missing to this project, just to make it perfect, is basically kind of have an obstacle avoidance system. Yeah, obstacle code, take into account basically when moving towards that outer wall.
Yeah, it's kind of interesting because I'm thinking about it in this way. So you have got a way that uses the very same sensor to find a wall, and once it does find the wall, it almost completely ignores everything that's in front of it, right? So yeah, maybe I'm not saying it correctly, but in that case, your implementation is interesting to me, right? In its robustness, it kind of like things that it struggles with. However, they're like we're nitpicking here, right? I already very much like it. So what I
Yeah,
was
yeah,
trying
yeah.
to find from your end is what do you think you could have done better? And I think your suggestion to say that maybe I'll have like an intermediate step where the robot tries to go around the thing that it considers to be an obstacle, but keep the focus on the wall. I know that's a lot of logic to get into the decision making of finding a
Yes.
wall, but already it's a very very good implementation. Let me say that. Yeah. And
Yeah, it's for example one case that we took into account for those type of cases is especially the it's hard, for example, once the this outer wall kind of approach fails,
mm,
once the robot starts, for example, facing a corner,
mm-hmm,
because what happens in this case is that the robot kind of finds let me just get close to the corner.
mm.
Um the robot uh the robot finds kind of two outer walls at the same time, so it can get
Ah,
distracted in terms of kind of which one to face. So if we run this project at the same time, what I do here is I have a previous step to finding the outer wall, where it's essentially what it does, it goes to the if it finds two outer walls which are both too close to each other and also like kind of very big segments,
right.
it goes to the most open space.
Uh-huh.
And once it finds the most open space, it goes like 30 centimeters away. Once it goes to the most open space, then it starts the outer wall finding process, and then it starts basically the wall falling process.
Mm-hmm, mm-hmm.
No, now it failed.
Yeah,
I think
that's
it's
because
because
of that thing. Yeah, the movable obstacle in
yeah,
front of it, right?
yeah.
Anyway, so let's talk a bit more about how you managed to have it go around the lab, right? So, are you using any form of
Mm-hmm.
controller, or you're just doing if then else?
I'm using mostly if then else controller. So
Okay.
essentially, if it's a very simple command where if, for example, there's two things that we take into account,
Right.
the the distance to the right and the distance to the left.
Okay.
If we get, for example, very close, let's say it's here right now, turning a corner, and we get very close to the center wall,
Mm-hmm.
then we start turning left. Um, and yes, otherwise otherwise we don't like we move forward. And if also one important thing, obviously, if it goes like within 2 centimeters of what my target kind of path is away from the outer wall,
Yes.
I make sure like it redirects just to make sure it like goes back to that starting position.
Mm-hmm, mm-hmm. Yeah, very, very well done, Mario. I'm really, really happy with your implementation. It it goes outside the box. That's what I want, because it shows that you can actually have the system find the wall in a way that is a lot more reliable than just saying, well, whatever thing is close to the robot is what it considers to be the wall, right? I consider that to be a not good, right? And this is way far from that. So that shows a lot of thought. You put a lot of thought into this. So very, very well done. So let's wrap it up here, and congratulations to you on your work. So just hang on for a
Perfect. Well, thank you very much. Perfect.
All right, everyone. This was Mario's presentation, and I'd like to encourage all those of you who would want to try this course, ROS2 Basics, using Python. You can also do the same thing, and you can come and showcase your work like Mario did. And until next